Okay, let's move on to the next application, which is the application in gauge theories. Now, gauge theories are theories of fundamental particle physics. So all the fundamental forces, the fundamental, forces of nature, except we are not exactly sure about gravity, so I'm going to say except perhaps gravity, are described by a kind of quantum field theory known as gauge theories. Okay. So gauge theories, these theories are invariant under action of some compact Lie group. I'll tell you what compact means when the time comes. Lie group, compact Lie group, where the group elements are functions of space-time. Okay, that's what the gauge means. So essentially, this result, this is so we need group theory to describe fundamental particle physics. So that's the lesson. And finally, but not least, last but not least, is Noether's theorem. So Emmy Noether was a very famous German mathematician, and she had to face a lot of sexism and a lot of discrimination in her time against women to have a very successful mathematics career. So she proved a theorem, amongst other things, and it says that, it's a theorem in classical field theory. And what she showed was that for every continuous symmetry, of the action is the integral of the Lagrangian, if you don't know. For every continuous symmetry of the action of a classical field theory, so if you're saying what is a classical field theory, think about electromagnetism, electromagnetic field. So for every continuous symmetry of the action of a classical field theory, there exists a conserved charge. Okay. So that theorem formalizes the fact that, in nature, we see conservation laws, right? Can you guys tell me some of the conservation laws?
Energy.
Okay. Conservation of energy.
Momentum.
Okay, momentum.
Electrical charge.
Electric charge.
Color of quartz.
Color of what?
Quark.
Quark. Okay, anything else? So this is basically a generalization of electric charge. What about angular momentum? Is that conserved?
Yes.
Okay, so what Noether showed that for every conserved quantity, there is a symmetry. So energy is conserved means that your theory is invariant under translation under time. That means that your theory doesn't depend on whether it was today or tomorrow you did the experiment. And Noether, and it also shows that momentum is conserved as a consequence of space translation. Electric charge is conserved as a consequence of a phase symmetry. And color of quark is a consequence of a non-abelian version of phase symmetry. Angular momentum is a consequence of rotational symmetry. Now, this is in classical field theory. In quantum field theory, we want to quantize these theories eventually. In quantum field theory, many of these, symmetries are unbroken. Symmetries remain unbroken. And then we get, we get quantum version. We get quantum version of conserved charges. So what does that mean? Means that for every observable that is like, these are called charges, we have some Hermitian operator Q. And that Hermitian operator in some state of our quantum theory has some expectation value, say Q. Then in quantum mechanics, Noether's theorem tells us that if this was a symmetry, if this charge was a result of a symmetry, then that would not change with time. Okay? So we will, I think we will prove Noether's theorem in some form. So yeah. Any questions?
Is this related to the probability charge density conservation?
No, it's not.
Sir, what about spin angular momentum?
Yeah, spin is also conserved. Yeah. Yeah, so you can add spin to this. But it's conserved if the theory is invariant under, say, that transformation. It could be that your theory is coupled to an external source, which is breaking that symmetry. If that is the case, then that's not going to be conserved, right? So, we see stuff like this. If you have done any physics, you know that the hydrogen atom Hamiltonian is rotational invariant, but when you put it in a magnetic field, then you get a term in the Hamiltonian which breaks that symmetry. So it depends on the interaction as well. But yeah, in general, spin should also be conserved. It's one of the possibilities. Okay, any more questions?